Right, good day, ladies and gentlemen. Welcome to the Physics Paper 1 revision video. Really glad for you to be able to tune in with us today. And what I'd like us to do is to go through 4 physics topics that come up in the Paper 1 exams. So this would apply to Year 10s for their mock exams coming up, or the Year 11s, separate students, combined students, all alike. Okay, so let's get started then. We're going to have a little look at energy. Okay, these are the topics coming up in this energy topic. You can pause it there and just have a read of those if you want to. Otherwise, I'm going to get stuck straight into energy stores and systems. Okay, energy stores and systems. So one of the most important things to do with energy is that energy can't be created, it can't be destroyed. It can only be moved from one place to another. It's one of the basic rules of the universe. Now, in this energy stores and systems topic, they might use the word system. System is really just a thing or things you're looking at. So, for example, a system could be a ball falling or a can full of gas. Okay, a closed system just means one where no energy or matter can enter or leave the system. Energy is only transferred between these stores. So these are stores of energy where energy can be held in it or it can be moved between these. So thermal energy is like heat energy, kinetic energy, also known as movement energy. Gravitational potential energy, that's energy due to the height above the ground. Elastic potential energy, the energy inside springs and elastic stretchy things. Chemical energy, things like petrol, foods, inside glucose. Okay, magnetic energy, that of magnets. Electrostatic, so that'll be the energy in electricity or stored in an electric field. Nuclear energy, that energy inside an atom. Okay, so those are the 8 different types you need to know about, and energy can transfer between those types. So energy can be transferred by heating, or we can say that energy can be transferred by doing work. Now when we talk about doing work, that means the same as the energy transferred. So we've got a kettle is transferring heat energy, so there'll be some electrical energy arriving in the wire. That electrical energy will be transferred into heat energy in the filament, and that heat energy will go into the water. So that's how energy can be transferred there. And the number of joules of energy, of electrical energy, will be transferred into the number of joules into the water. But also there'll be a little bit of sound as well that comes out as wasted energy. So here are some examples of how we can do work to transfer energy. Well, when we throw a ball upwards, there is chemical energy inside his arm, and that chemical energy inside his arm will be transferred into the kinetic energy of the ball as he throws it upwards. As the ball starts to fall back down again, gravitational potential energy in the ball will be transferred into kinetic energy as it falls. A speeding car, which is hot on the brakes there, as you can see with our the red glowing brake pads there. Well, when we look at that, we can see down here that that's glowing red because we're transferring kinetic energy into thermal energy that's inside the tyres there. And when we crash a car, we're transferring the kinetic energy, transferring that into kinetic energy to make the crumple zones crumple. So that moving metal as it crumples, that's changing the speed into transferring that energy into the crumple zones and down here. Okay, so energy cannot be created or destroyed. It can only be transferred from one place to another. So this means that the total energy I put into a system has to come out as either useful energy or some wasted energy. So the total energy I put into my TV is the same as the total energy that comes out. And we've got to include there our wasted energy as well. So not only will light and sound be coming out of the TV, which is really useful, out the speakers and the screen, but there will also be some wasted heat energy that comes out normally out of the back, and you can feel that if you put your hand down the back of electrics, you can feel that they are generally warm. Now, not only is the total energy equal to the total energy out, we can also think of this in a closed system. So all I mean by that is like a room where the door is and the windows are shut. So when a hot pie, you take it out of the oven of one room and you put it into a cool room, well, what's going to happen there? The energy that's stored in the pie, in the thermal store of the pie, that energy store is going to go down. And it's going to transfer that energy into the energy store of the room, which is going to go up. So the room is going to warm up just a little bit, the pie is going to cool down quite a lot. And the total energy of both, when you include both of them in, the total energy stays the same. Okay, so conservation of power then. Conservation of power is the rate of doing work. So the rate of transferring energy, how quickly I'm using energy or transferring energy. So two equations for this. We've got power equals energy divided by time, or power equals work divided by time. Remember that power and work, work done and energy transferred are the same things. Okay, so our two equations then, look, they've even got the same units, just to prove that they are the same thing. Okay, so there's something you need to know with power. You need to be able to describe how two machines with the same machine rather with two different powers, how it will do its job differently. Now we can say that both of these hairdryers will be able to do the same amount of work. They can both transfer the same amount of energy. They'll both dry the hair up eventually. But one's got a higher power rating than the other. That'll be this lucky lady here. And the one with a higher power rating is going to dry her hair more quickly. It's going to transfer the same amount of work to dry the hair, but it's going to do it more quickly because it's got a bigger power. And the reason for that is that we're dividing our energy transfer by time. So the shorter the time, the bigger the power. Okay, the shorter the time, the bigger the power. Okay, so kinetic energy and potential energy. So kinetic energy, we all know that that's movement energy. Well, there's an equation you need for that. So kinetic energy, measured in joules, is equal to half, or 0.5, times mass, times velocity squared. Okay, so that's velocity times by velocity. Okay. Now, gravitational potential energy, so the energy due to the height above the ground, is potential energy equals mass times gravity times height. Now the unit for these then are down here. We've got gravitational potential energy in joules, mass measured in kilos, gravity field strength in newtons per kilo. You'll be given that in the exam. You don't need to recall that number. And the height as well. Okay, so for example, we've got someone jumping off of a cliff. They have gravitational potential energy stored in them at the top because of their height up here, and this will transfer as they fall. This will transfer into the kinetic energy. The further down they fall, the faster, the higher the kinetic energy, until they land very safely at the bottom there, I hope. Okay, so how do we reduce unwanted energy transfers then? So energy transfer is basically wasting energy. How do we reduce that? So this basically means that we're wasting less energy. Okay, well, if it's got moving parts, put some oil on it. So lubricants, they reduce the friction on moving parts, meaning less energy is going to be wasted as heat. Because of course, friction causes heat, like rubbing things together causes heat. So how else can we reduce unwanted energy transfers? We can put insulation around a boiler. We could maybe make our kettle have a silver inside so that it reflects heat radiation back into the kettle, meaning more heat will get transferred into the water. So insulation, for example, foam, wool, shiny silver, fiberglass, they're all going to reduce heat loss, and that means that less energy will be wasted as heat. So very useful. Okay, conduction and convection. So what is conduction then? Well, when I heat up, for example, maybe at the end of a metal rod, you can imagine these as the particles of that metal rod. As I give them more heat to start off with, only the very nearby particles are vibrating more, but gradually every particle next to that will start to vibrate more as they collide into each other. They're going to bump into each other and pass on this kinetic energy until eventually the whole rod would end up being heated and warmed. Okay, convection currents are the movement of warm fluids. So that could be gases or liquids. They can both have convection currents in, where your air particles rise up because they're less dense and sink back down because they become more dense once they've cooled down. Okay, so convection is moving air particles. Conduction is the vibrating particles of a solid, and conduction happens best in solids because they're close together. Okay, houses have got insulation to stop these two methods of heat transfer. Now air is a poor conductor, so having air trapped in a foam in a gap between an outer wall and an inner wall reduces heat loss. This is called cavity wall insulation. So that's putting foam or polystyrene beads in a gap between an outer wall and an inner wall. Loft insulation, that's going to stop convection currents forming in the loft because you've got a layer of nice thick trapped air just above your ceiling. Double glazing has got a vacuum layer. Now vacuum is really important, you know, that's got no particles in it. So a vacuum, we're not talking about a vacuum cleaner, we're talking about a vacuum like you find in the emptiness of space. So that's going to stop both conduction and convection. And people often forget about these. So draft excluders is the thing, the little doggy shaped thing that your gran has got at the bottom of her door to stop the drafts. Okay, efficiency. So there are two equations, two different ways of working out efficiency. There is working it out as a decimal, and there's working it out as a percentage. So if it's a decimal, it's going to be a number between 0 and 1. Okay, 1 being really efficient, 0 being awful, no efficiency whatsoever. And then as a percentage, you're going to have a number between 0 to 100%. Okay, now we can talk about efficiency either in terms of energy, so useful energy out of a TV over the total energy you put into a TV gives you the efficiency, or we can think of it as power. So the useful power out of my Hoover divided by the total power I put into my Hoover. Very interesting. Okay, the useful energy out will hardly ever be the same as the total energy in, because energy is nearly always wasted. So for example, friction of moving parts, unwanted sound or light given off. And most wasted energy is lost as heat to the surroundings. So most pieces of equipment end up warming up the air around it, and that eventually will just be dissipated and will just be spread out into the surroundings. Okay, so energy resources and their uses. So energy resources fall into two categories: renewable and non-renewable. Non-renewable. So renewable means it won't run out, non-renewable will run out. And when we look at the renewables, these examples, you all know these really well. Just a couple to maybe focus in on. Hydroelectric is falling water, that's a river going down a mountain. Biofuels, well they're bio as in biology, living plants and animals, or dead plants and animals rather. For example, crops, tidal power, the tides coming in twice a day. Geothermal, geo meaning rocks, earth, thermal meaning hot, so hot rocks under the ground. And these are all free energy once you've set them up. They're not always reliable, these ones. Some of them depend on the weather, particularly wind power, particularly solar power. We may need lots of them to supply our energy needs. Okay, so non-renewable ones, coal, oil and gas, these ones will run out one day. And they damage the environment by producing carbon dioxide, which causes global warming. And they currently provide most of our energy needs. Okay, so they're really important to us, but they're bad for the environment. We've got to be super specific about that. They release CO2, which causes global warming. And there's another one which is non-renewable, would also run out, but not so quickly, in a few thousand years. That's nuclear energy, and where we have lots of energy from a small mass of fuel. 1 kilo of uranium will make a lot of electricity, and a small risk of disaster. So there's not much chance of it happening, but when it does happen, it's very bad. For example, Chernobyl in the Ukraine. So there are no polluting gases from this, and we've got to be really clear about that. It doesn't produce carbon dioxide. We're not burning anything, so there's no need to talk about carbon dioxide here. There are no polluting gases with nuclear. We can also use energy resources for transport and heating. So when we use them for transport, biofuels are used more and more for vehicles. So biofuels, such as your crops being used to produce ethanol, they can be used more and more for vehicles. And we've also got using renewable power for heating, solar water heaters on people's roofs, burning biofuels, that could be just burning wood in a fireplace, or a geothermal heat pump to heat buildings. So that's hot rocks heating up the water under the ground. Now non-renewable as transport, non-renewable energy is used. Petrol and diesel are created from oil, which still provides most of our transport needs. So these two are our most common forms of fuel used for motor vehicles. And non-renewable is heating, so how we heat our homes using non-renewable, well, burning gas is the most common use. So gas boilers heat up water and pump it around our radiators. Coal is often burnt in fireplaces, and electric heaters, they'll be plugged into the mains, and so they use electricity from non-renewable sources in the most part. Okay, so trends in energy use then. Trends means like how things, the pattern of how our energy use is changing over the years. So we still depend on fossil fuels. They're used to create electricity, and the demand for electricity has increased in the last 100 years, but it is starting to slow down as we become more careful about how we use it. So we want to use more renewable resources. we want to use more wind and solar and wave power, burning fossil fuels releases carbon dioxide, which creates global warming. Things which are really our biggest threat probably to mankind at the moment. This increase of temperature threatens us with melting ice caps, rising sea levels, changing weather patterns, and governments have signed up to agreements to reduce the use of non-renewable resources. So there is the Paris Climate Agreement that all nations signed up to recently, I think it's 2016, and the US has recently decided to pull out of that, although many people are hoping that they will rejoin that. So that's an agreement to reduce the use of fossil fuels in order to reduce the global warming, the effect of global warming. Using more renewable resources is limited because of how reliable it is. So if we can't use lots of solar power in a place where it's not very sunny, we can't use a lot of wind power if it's never windy. So how expensive the research and the installation is, that is a limiting factor. It reduces the amount of resources that we're trying, and the difficulty of international politics between countries. So as I was mentioning there, the US pulling out of the Paris Climate Agreement. Okay, so specific heat capacity. I've left this till the end of the topic because this is a part where we really want to try and focus to get just a few marks in a 6-mark question related to this. We don't feel like you have to get the entire method correct, that you have to aim for 6 marks or nothing. So let's have a look at this required practical to see how we can pull out marks on this. So definition of specific heat capacity. The specific heat capacity of a material decides how much energy it takes to increase the temperature of a kilo of that material by 1 degree Celsius. So the equation for this is the energy required is found by the mass of that object, as we said the mass is involved, times by the specific heat capacity, times by the change in temperature. Okay, and here are our units, so energy in joules, mass in kilos, specific heat capacity, joules per kilogram degree Celsius, and this theta thing up here, that egg-shaped thing, is the temperature change, okay, in degrees Celsius. Now, if we have a look at the practical here, well, what have we got here? This is a rough diagram showing us how we're going to carry out a practical to investigate the specific heat capacity of this block. So this is a metal, and we want to find out how much energy does it take to increase that temperature by 1 degree. So to do that, we've got our thermometer here, we've got our metal block on the inside, and we've insulated it. It's a really important idea that we put insulation around the outside so that the heat we're putting into the block stays in the block and doesn't come out and warm up the room. We don't want that. So what else have we got? We've got a power supply here providing our electricity. This here is our heating element, so our electricity is going to be transferred into heat inside this metal block. Now up here we've got 2 things. We've got a voltmeter and we've got an ammeter, because they're going to help us to work out the power, the energy transferred. They're going to help us with this energy transferred bit over here. Okay, so let's have a look at this then. So these are our 2 pictures from the previous slide, and let's have a look at a potential method for how to find the specific heat capacity of a material. And again, don't feel like you need to get every single part of this to get 6 marks. If we're hitting 2 or 3 marks, we'll be doing really well on this type of question, because it is a nasty one. So how to find the specific heat capacity of a material? Firstly, weigh the block. We need to know from the equation, if you look at the equation closely, we need to know the mass. So measure the mass. Okay, we can all remember to do that. Insulate the block, wrap it up, take the starting temperature. If you think about finding this number here, our change in temperature, that's got to come with taking the starting and the final temperature. So easy marks so far. Weigh it, take the starting temperature, at the end take the final temperature. Okay, so we're going to turn on the heater, we're going to time how long the heater's on for. Now take the ammeter, that's going to give you the current, and the voltmeter, it's going to give you the voltage, and then use power equals current times voltage to calculate the power of the heater. Once we know the power of the heater, we can then use energy transferred equals power times time to calculate the energy transferred to the block. That will tell us over here, that will tell us our E, or energy transferred, leaving us to be able to rearrange this to find C. So take the final temperature, calculate the change in temperature theta, now rearrange the specific heat capacity equation to find C. So C equals E over M times theta. Like I said, don't feel like you have to get all marks there, but just think about how am I going to take some readings here to be able to work out the missing variables of the equation for me to find C. Okay, topic 2, electricity. Topic 2 contains current, circuit symbols, resistance, LDRs, series circuits, parallel circuits, electricity in the home and national grid. So let's get stuck in. Okay, here we have some common symbols. Now, which ones are maybe the ones we might sometimes struggle to remember? Okay, so diode. The job of a diode is to only let electricity through in one direction. So that's why it's got a little arrow and it's being in a little flat line there. So in your circle is an arrow with a flat line that's telling us which direction it's going, and it won't flow backwards again. Thermistor, just like a resistor, but instead it's got a diagonal line, flat bit at the bottom, as if that's maybe like a heating graph or the line of temperature going up there. LDR is another one you need to know. So LDR has got our little rectangular box, circle around it, and it's got our two little arrows coming in. Now, if this is a light-dependent resistor, what do we think those little arrows represent? They're the light going into it. Variable resistor, that's our arrow going through there to show that we can change that. Okay, so what are the circuit rules? We must have a closed loop. We must have a circuit that goes round in a loop, and it must include a source of potential difference. So having a look here at this basic circuit, we've got current, which is one of the most important parts of electricity. Current is the flow of electrical charge. It's the flow of electrons. Current is slowed down by resistance. So anything that resists the flow of electricity, we call resistance. Now, the bigger the resistance, the smaller the current. Because of course, if something's resisting that current, current's going to get less. So current equals, charge, the flow of charge equals current times time. Or another way of writing it, current equals the rate of flow of charge. So Q over T, how the charge is given out over time. Okay, charge is measured in coulombs, current is measured in amps, and time in seconds. Okay, so resistance then, how do we calculate resistance? Well, you need to be able to make a circuit to be able to measure resistance. So we can't measure it directly. So what we have to do is we have to use V equals I times R. So we can rearrange this to find R. We're going to have R equals V divided by I. Okay, so R equals V divided by I. And we need to place our ammeter in a specific place. The ammeter has to be in series with the circuit, so all in on the loop. And a voltmeter, though, that's measuring the potential difference across the component. So we have to have our voltmeter in parallel. So you notice here the wires come off of the sides of the resistor that we're trying to work out the resistance for. So to find the resistance of an unknown component, rearrange V equals IR to R equals V over I. And resistance measured in ohms. And current is measured in amps, voltage, potential difference is measured in volts. Okay, so LDRs and thermistors then, what do we need to know about these? Well, an LDR is a light-dependent resistor, so it's a resistor that depends on light, and it is often used in street lighting. There's a little bobble at the top of it there, so that turns the light on and off when it's dark or light. Now we have an actual LDR just here. Not that you need to know what they look like, but you do need to know the symbol for it. So there's our LDR, that's our light coming into our component there. You also need to know the shape of the graph. So the shape of the graph is that increasing the light intensity, as that one goes up, that resistance goes down. So you need to know the shape of that graph, and thankfully thermistors have got the same shape of the graph. So as the resistance goes down, the temperature goes up. Okay, and there is our thermistor, that's what they look like. This is the symbol for it. You don't need to know what they look like, but you do need to know the symbol. And you also need to know some examples of where they happen. So they occur in kettles, so when it gets too hot, the kettle turns itself off, and in a thermostat as well. So for example, when it gets too cold, your heating can come on. Current is the same at all points in a series circuit. As we can see here on this circuit, we've got a current of 0.5 amps flowing past each of the ammeters. So 0.5 amps will flow past the cell, will flow past the bulbs. Current is the same at all points. Voltage in a series circuit, so a series circuit being an all or nothing circuit where either everything works or everything doesn't work. You can't have one component still working and another one broken. So voltage gets shared between these components. So voltage in a series circuit will be if there are 4 equal resistors here, 3 equal resistors, we'll have a voltage of 4 volts because it's 12 divided by 3 equals 4. So that voltage is shared between the components. Okay, again, series circuit, so all or nothing circuit. So here the resistances will add up. So the resistance of that resistor will add together with that one to make the total resistance. So whatever they are, you just add them together if they're in series. Same with cells in series. So a cell is just one of a battery. So when you get lots of them, they're called a battery. So these will add up when they're in series like that. So 2, 2 and 2 will make 6. Okay, parallel circuits. So current down the branches in a parallel circuit, parallel meaning like parallel lines. In a parallel circuit, the currents down the branches here, and these are the branches because that's my cell there. These are the branches. The current down the branches will add together to the current past the cell. So we've got 18 amps past the cell, and we've got 3 equal bulbs, so 6 amps down each branch of the parallel circuit. And you can also see there that there's another example, slightly harder. This is with different power resistors, and we've got 0.05, 0.15, 0.10 amps. You can add those 3 together, and so we're going to have 0.3 amps going past our cell. Voltage is the same down each branch, so each branch here has got the same voltage as the voltage past the battery. Okay, so the voltage past that is the same down each branch. Okay, what else do we need to know about parallel circuits? Well, adding resistors in parallel to each other, so adding a resistor in parallel instead of in series, that just reduces the overall resistance. Okay, just makes the overall resistance go down. The reason for that being is there are now more paths for the current to flow down, so there is less resistance. So for example, just one 2 ohm resistor here lets through a current of 1 amp. Well, if I was to put even a weaker resistor next to it, over here a 1 ohm resistor, well, I'm going to get some extra current through here, include that to my extra current through here, meaning that overall past the cell I'm going to now have 3 amps, so a bigger current because the resistance has been reduced because I've got them in parallel. Here we have electricity in the home. Mains electricity, some important numbers about them. We have an AC supply, alternating current, flips backwards and forwards, and it flips backwards and forwards 50 hertz per second. So sorry, 50 hertz, which is 50 times per second. And the potential difference that comes in through the mains is 230 volts. Okay. Now a plug, you need to know how to wire a plug. So knowing the colours will help you to know where they go. So striped, the stripy green and yellow one, that goes at the top. The second yellow of striped is T. Blue goes to the left, and brown goes to the right. So blue, brown and striped. Now there are 3 wires unless your appliance is double insulated. Double insulated means that it's got a plastic coating on the outside. So you might see a hand drill for drilling holes into the wall. If that's completely made of plastic on the outside, it may only have 2 wires and it won't need an earth wire. Now the earth wire, how that helps us, well, the earth wire connects to the metal case of an appliance. If the live wire comes loose, the current flows down the earth and not through you. It completes this, the neutral wire, the blue wire, completes the circuit. So if you imagine that you have a cell, and the live wire is taking it to our appliance, whatever the appliance might be, it could be a bulb, well the neutral wire, the blue wire, is going to be the one taking it back to the battery, in other words, completing the circuit. Okay, our live wire is also providing an alternating current. That's where the energy is coming in of. It's got a voltage of 230 volts, okay, and it can give you a shock. That's important that you're able to explain that. Now our neutral wire carries a voltage of 0 because it's coming back to the cell. It's not bringing any voltage with it. Okay, so how to calculate the power of appliances then? A lot of equations on this slide, but in a nutshell, what have we got here? So potential difference, voltage, is the energy transferred by charges. So energy is the charge times the voltage, and voltage is the energy transferred per charge. Okay, same equation, just rearranged. So energy is measured in joules, charge in coulombs, voltage in volts. So there's 3 different ways of calculating power for electrical appliances. We've got power equals energy divided by time that we've seen before. Power equals I squared R, so current squared times resistance. And we've got power equals current times voltage. So P equals IV, P equals I squared R, P equals E over T, or P equals W over T. So the national grid then, this is our electricity distribution network. So the national grid is made up of these parts. It's made up of a step-up transformer, it's made of our cables, and it's made of our step-down transformer. So the step-up transformer, the job of that is to increase the voltage to reduce energy loss in the cables as heat. So it reduces energy lost as heat. Step-down transformer, just before the house, before our homes, that reduces the voltage back to safe levels for households. So step up increases the voltage to reduce heat loss. Step down reduces the voltage to make it safe again. Topic 3, particle model of matter. So we're going to be looking at in this topic calculating density of materials, internal energy, changes of state, and specific latent heat as well. Okay, let's get going. The particle model. So what do we know about the particles in a solid, in a liquid, and in a gas? So what can we say about the energy of the particles? Well, as they go from solid to gas, so we can imagine this as maybe water. We've got our ice, and we've got our normal water. We've got our steam up here. And check out my handwriting. Yes, it's like a toddler. So there is my steam. Okay, so we've got our ice all the way up to steam. Energy of the particle goes up as we go from solid to gas. The arrangement then, so here they are all touching. Liquids, they are partially touching. Gases, they are not touching. They're far apart from each other. What about the forces of attraction then? Well, solids, they have strong forces of attraction. That's why they are so close together. Gases, really weak forces of attraction. In fact, they've broken their forces of attraction. That's why they're not touching each other, they're not connected. And the distance between the particles, that also goes up. And the shape of them, so these ones will sit at the bottom of a container. Liquids will fill the entirety of the bottom of a container, and gas will fill up the whole of a container. Okay, so how can we use the particle model to explain gas pressure then? What is gas pressure? Gas pressure is caused by particles hitting the walls of a container. They're hitting the walls, and that provides the pressure that we feel when we squeeze maybe on a bicycle tyre. It's a measure of the force of those particles per unit area. So force over area. So pressure equals force over area. And here we see that the forces are at right angles to the direction of them hitting the walls. So we can increase gas pressure in 3 different ways. We can increase the temperature, and each of these ways will make more collisions happen with the wall. So increasing the temperature means they move faster, hit the wall more often. Reducing the volume, so making the box smaller, will mean that the particles hit the walls more often. Putting more particles in will mean more particles hit the walls more often. So density then, what is density? Density is basically how much mass is packed into a volume. The more mass you pack into a volume, the bigger that number is, the bigger the density. Okay, the smaller your volume, the smaller that is, the bigger the density. So you put mass into a smaller volume, you've got a bigger density. And that is rho, that's the unit, the symbol there for density. Rho equals mass divided by volume. mass in kilograms, volume meters cubed. Okay, giving us our density in kilogram per meters cubed. So we can calculate the volume of a regular object like a cuboid by doing width times length times height. We can find the volume of a liquid really easily. We put it into a measuring cylinder, and 1 milliliter on our measuring cylinder is the same as 1 centimeter cubed. So that gives us our volume really easily. Now, if we want to take find the density of an odd-shaped object like a Lego man, so for each of these equations, whether we're doing the cuboid, a liquid, or the Lego man, we need to be weighing them on a set of scales first to find their mass. So we just basically need to find these things in the equation. So we can calculate our volume by doing width times length times height, or from a measuring cylinder, or by dipping our Lego man into our Eureka can here. And when you put the Lego man into the water, he will shift an even volume of water, an equal volume of water to his volume. So out will come water, and we can collect that in a measuring cylinder. So that water goes into here, and that will tell us the volume. So internal energy in changes of state then. What is internal energy? It's the combination of the particle's kinetic energy and its potential energy due to their position or their state of matter. So when you heat something up, the temperature changes. And the temperature change depends on the mass of it, the mass of the object, the material, the specific heat capacity, for example, and the amount of energy you put in. So when we heat something up, the mass of it and the material of it will decide the temperature change. So we can see our changes of state here. We've got melting when it goes from solid to liquid. We've got evaporating when it goes from liquid to gas. When it goes back again, we've got condensation, and up here we've got liquid into freezing liquid into solid is called freezing. Now we can have particles skip out the liquid phase, and we call that sublimation. And we can also have a gas go straight back into a solid again, and we call that sublimation. Okay, they've both got the same name. We can see there the different states of matter as we go through the changes of state. So we can see also that our particle speed increases as we give it energy. Okay, so latent heat then. What is latent heat? Well, if we have a look at this graph over here, this is a graph of showing our temperature against the time that we're heating something up for. So this is basically the amount of heat provided going that way. So when something's a solid, we provide heat, the temperature goes up. When it starts to melt, when it hits its melting point, we're still giving it heat, but its temperature staying the same. With our liquid state, we're giving it heat energy again, so its temperature is going up. And then when it's changing state, the temperature stops changing until it has all changed state, and then the temperature can keep going up again. Now these flat parts here, these flat parts is where energy is being supplied to change the state. So the energy is being supplied to change the solid into a liquid. The temperature is not changing in that point, but it is changing state. And the same up here. Energy is still being provided, but it's not changing state. The temperature is staying the same. So the specific latent heat, when we look at this equation over here, the specific latent heat is the energy needed to change the state. It's the energy of the flat bit of the graph. Okay, so the energy required there to change the state is found by the mass of that object, the mass of that liquid or gas, times by the property of the liquid of the specific latent heat. So just like specific heat capacity, each material has got a unique number that helps us work out how much energy it takes to change the state of it. Okay, so topic 4, atomic structure. In this we cover the developing model of the atom, isotopes, nuclear equations, half-life, and irradiation and contamination. So when we look at developing the model of the atom, the ancient Greeks had the idea of uncuttable, indivisible, small units of matter. You chop them up into atoms and you can't chop them up anymore. In 1897, so just over 120 odd years ago, J.J. Thomson proposed the plum pudding model. Well, what is the plum pudding model? It has got a positively charged dough, like the cakey element of the plum pudding, and that's all positively charged, and then we've got little electrons spread randomly throughout it. As we can see, this is really different to the model that we now know. So how did the model change from this plum pudding model into our new model? Well, here comes the Rutherford and Marsden's gold leaf experiment. So this was where a beam of alpha particles was fired at a really thin layer of gold leaf in here. And we can see here that a lot of the particles went straight through, some of them were deflected a little bit, and a very small number were deflected back by more than 90 degrees. So what does this tell us? Well, the most that went through undeflected, if we look at these atoms here, most went through deflected, meaning that mostly empty space inside an atom, 99% empty space. The small number that deflected a little bit, well, that tells us, because alpha particles are positively charged, they've got positive charges because they're made of 2 protons and 2 neutrons, it shows us that the nucleus must be positively charged. Okay, otherwise they would have been attracted towards it, but instead they were deflected a little bit. Now a very small number deflected by more than 90 degrees, they actually came back out of the gold leaf backwards. And this tells us that the nucleus is very small and concentrated as well as positive. So if the nucleus was big, lots of the alpha particles would have been deflected backwards. They weren't, only a tiny number were. Okay, so what do we know about the nuclear model then? The nuclear model says it's a small concentrated nucleus. We've got positive protons and neutral neutrons on the inside in here. We've got negatively charged electrons orbiting at distances called shells or energy levels. And we know that we can fit 2 electrons on that first inner shell, 8 in the next one and 8 in the one after that. Now, electrons can go up an energy level. If they receive electromagnetic energy, they can jump up a level so they can get to a further out level, or they can go down a level if they give out some energy. So the further away from the centre, the higher the energy, the lower towards the centre, the lower the energy. Now we also know a few other things about them. Protons have got a plus charge. Neutrons, neutral, 0. Oh, and of course, protons start with the letter P, so they are positive. And electrons, they're negative. They're a negative -1 charge, and they're masses. Don't forget that when we look at, for example, C12 and 6, we've got our massive number, the bigger of the 2 numbers up here. That tells us the number of particles in the middle. It's also telling us the mass number because each particle weighs 1. Each particle has a mass of 1. And our electrons, we can say it's nearly nothing. We can say it's close to 0 or it's nearly nothing. We don't have to quote the 1/2000. Okay, so what is an isotope then? An isotope is a version of an atom with a different number of neutrons. Here are 3 examples of isotopes. We've got 3 different versions of carbon, carbon-12, carbon-13, carbon-14. And I'm quickly working out those mass numbers because I'm adding together my protons and neutrons. And I know that each one of these is carbon because they each have 6 protons in the middle. It's the number of protons that decides what the element is. So if it has 6 protons, it is carbon. Okay, if it has 7 protons, it is nitrogen. Round the outside, they should have the same number of electrons. The number of electrons is not affected by being an isotope, but what they do have is they do have different numbers of neutrons. So we've got 6 neutrons, 7 neutrons, or 8 neutrons. Doesn't affect how they react. They'll still react in the same way in chemistry. Doesn't really affect much. Just occasionally, if they've got too many neutrons, they become unstable and they may release radiation. Okay, so some of them are unstable. They can decay and give out nuclear radiation. Okay, so isotopes and nuclear radiation then. What do we know about our 3 types of radiation given out of the nuclei of unstable atoms? We can get alpha radiation, beta radiation, gamma radiation. These are our Greek letters here. It's basically like a little A. There's like a capital B with a tail, and there's like a squirrely Y. Here are our symbols for them. Well, this tells us that alpha particles are a helium nucleus. It's exactly the same as a helium nucleus because it is a helium nucleus. It's made of 2 protons and 2 neutrons. Our electron that comes out of the nucleus is a high energy electron, slightly different to the ones that go around the outside, but not much. And that is literally just made of an electron there. And our gamma radiation, that is our electromagnetic wave. Now they've got charges because they're electrically charged. This has got 2 protons in the middle, no electrons, so it's got a +2 charge. Our electron has a -1 charge, and our gamma radiation, because it's not a particle, doesn't have a charge. Now each one of these is stopped by a different material. So alpha radiation, being the heaviest and the slowest travelling, is stopped by a thin piece of paper. Our beta radiation is stopped by a thin sheet of aluminium, and our gamma radiation is stopped by a thick piece of lead. See, we can also see that reflected up here in our table, and we can also see the range that travels in air. So alpha radiation travels just a few centimetres, beta radiation up to a metre, gamma radiation a really long way up to a kilometre. And they've got different ionising powers. Now, ionising power is about stripping electrons, the power to strip electrons from atoms. And alpha radiation, because it's got a positive +2 charge, is really highly ionising. So that's very dangerous if you were to get it on the inside of you, as it would keep on stripping electrons from your DNA, and that could cause cancers. Our beta radiation is also ionising, but not quite as much as alpha radiation, because we can see that also has an electrical charge. But our gamma radiation doesn't have much ionising power, it's very low, but of course it's still dangerous because gamma radiation passes straight through us. Okay, alpha and beta particles are deflected by an electric field. So beta radiation will be attracted to a positive plate of an electric field. Because beta has a negative charge, it's going to go to the positive. They're attracted. And our alpha radiation, because it's a positive charge, is going to be attracted to the negative plate. Gamma radiation has no charge, so it will pass straight through undeflected. Now, nuclear decay equations, we can actually... That's the wind blowing my blinds over there, excuse that. So, nuclear decay equations, alpha, beta and gamma radiation are all emitted by the nucleus. They all come out of the nucleus. Now, when an alpha particle comes out, because it's made of 2 protons and 2 neutrons, it's going to make my mass number go down by 4. It's going to make my atomic proton number go down by 2. Now, a beta particle, the mass number is going to stay the same. And the atomic proton number is going to go up by 1. And the reason for this is that when a beta particle comes out of the nucleus, a neutron is turning into a proton, and it releases that electron. So when a neutron, which has a mass of 1, turns into a proton, which also has a mass of 1, the mass number stays the same. But because there's now a new proton, the atomic number or proton number goes up by 1. Okay, gamma radiation is a high energy electromagnetic wave, so it has no effect on the mass number or the proton number. Now over here we've got some examples of nuclear decay equations. You'll have to calculate the new mass number and the atomic number. That's the mass number and that is the atomic number. So we're going to have to calculate those two numbers. So let's see how we would do that. So if they told us that uranium-235 92 is going to decay by releasing an alpha particle, you've got to reduce the top number by 4 and reduce the atomic number by 2. Because as we can see over here, that number plus this number has to add up to that number. Okay, so we have to keep it balanced in that regard. So now let's have a look at a beta particle coming out. In a beta particle, as we say over here, let's clear all this off, as we say over here, in beta decay, mass number stays the same, atomic number goes up by 1. Mass number is 14, stays the same at 14, and atomic number goes up by 1. When it goes up by 1, it's no longer carbon, it's now nitrogen. Okay, so you just need to make sure that these numbers here, your 7 and your -1, balances to your 6. Over here, your 14 and your 0 balance to 14. And then when we release a gamma wave, there is no change to those mass numbers and atomic numbers. They stay the same. Okay, so calculating half-life then. So half-life of a radioactive material, we say it in 2 different ways. It's the time taken for the radioactive count rate to go down by half, or it's the time taken, another way of saying the same thing, the time taken for the number of radioactive atoms to go down by half. So how to calculate half-life from a graph? So if it's the length of time, here we've got our time going along the bottom there. If it's the length of time, for the nuclei number to go down by half, what we have to do is look and see what is our starting number there. Well, that is 100 nuclei, and that's going to go down by half. So we go down halfway, we draw a straight line across to the graph, and then we draw it down from the graph. Now you're going to use a ruler and do it neater than me, but you must show you're working with this because there'll be marks for that. So look at the starting count, half it, draw a line to the graph and down to the time. That is your half-life. So let's try again with this one here. Your counts per minute starts off as 80. So we halve that, 40, draw across to the graph, and then we draw down. So here my half-life is 2 days. Here my half-life is 10 seconds. Notice where I'm getting the days and the seconds from the units over here. Okay, now there's another way of looking at half-life, and that's to be able to work out from the starting count rate how the count rate goes down each half-life. So the radioactivity, or the count rate of radioactive rocks, goes down over time. They become less radioactive over time as the radioactive atoms decay into normal atoms. So have a look at this example. Half-life of a material X is 2 years. So every 2 years, the number of radioactive atoms goes down by half. Not divided by 2, not going down by the same amount each time, but by going down by half each time. So the count rate started at 240 counts per second, it would fall to 120, then 60, then 30, etc. and so on. Okay, irradiation and contamination. So to irradiate means to shine nuclear radiation like a torch. This is useful for sterilising medical equipment or treating cancer. So you can focus it onto some cancerous cells, or we can shine it like a torch at some equipment that needs to be sterilised. Alpha, beta or gamma radiation can come out in a stream and hit an object. Afterwards, the object is not radioactive anymore. So because it's the alpha and beta and gamma particles themselves that are coming out, there is nothing that stays on the materials itself. Afterwards, the object is not radioactive, and therefore it's not dangerous, as the alpha and beta and gamma will have been absorbed or released. So that is irradiation. Now, irradiation is different to contamination. To contaminate with radiation means that we have put radioactive atoms and we've attached them to an object, so that there is an actual lump of maybe uranium or plutonium or any other radioactive material that's attached to the object, and that's why we say contaminated. Now this can be useful sometimes, so it's dangerous because those objects can continue to release alpha, beta and gamma radiation even, unless you remove the contaminating material. So this can be really useful if you want to see inside a human during a medical checkup. So for example, a patient may drink a barium liquid to see inside their stomach, and here we have, there's a spine, here we have their small intestine here, and we can see the travel of this barium liquid through their digestive system, and that might be really helpful to see maybe blockages or issues. We can also check for water leaks in a sealed water pipe. So they would seal the ends off of the water pipe to find the leak. They would pump down a radioactive material, and we can call this contamination, to contaminate the water. And they'll be able to use a detector up above the ground to see where the highest amount of radiation is. And they'll notice that it's coming out from where the leak is. With more leak, there's more radioactive material there, so a bigger reading there. So both contamination and irradiation can be dangerous in the wrong situation, but also highly useful if it's got a purpose. And be prepared to explain in detail what it's used for and how they use it.